Okay, so good evening, everyone. This is going to be our fourth tutorial session on the NPTEL course on mechanism and robot kinematics. So as usual, I'll be reviewing some aspects, the week contents of week 3 and some aspects of week 4. And we would also follow it up with some MATLAB problems, and also I'll just try to uh, go through some of the sections, some of the information also contained in the book called Modern Robotics by Kevin Lynch, which I had mentioned in the first class of this tutorial session. So yeah, so let's start with what we learned during the third week of this course. So we had started with the displacement analysis. So displacement analysis, as is known to you, it consists of two aspects. One is what we call as the forward kinematics, and the second part is what we call as the inverse kinematics. So in the forward kinematics, what happens is, given some input, find some input, maybe I'll just call it I, find some output, maybe O itself. These are just some symbolic parameters. So given some input, we want to determine what is the output. So this is what is contained in forward kinematics. And in the inverse kinematic, it's it's quite straightforward. It's literally the inverse of this. So given output O, determine input I. This is what is contained in inverse kinematics. Right? So the goal of so far in weeks 3 and 4 is essentially this. We are looking at determining given input, we want to determine what is the output, and then vice versa. For inverse kinematics, it happens to be given some input. Our goal is to find the input. And this has been done for several different cases for 4-hour chain, which can consist of 4 rotation chains, which means that it has chain with 4 revolute joints, so to speak. And the goal was to do both for open chain and closed chain. So as of now, open chain, so we started with, first of all, we started with the constraint mechanisms, right? So let me just write it. So we have started with 4-hour chain. So 4-hour chain is our, say, the object of study. And then we look at, it's essentially a construction of 4 revolute joint, say 4 links, and of course connected by 4 revolute joints. So this is essentially the goal, and one of which is fixed, which we call as ground. So this is ground link 1, ground link, this is the link 2, link 3, and link 4. And these are all revolute joints. So we have 4R, and that's the reason we call it 4R. So the goal was that given some input, we are determining some output, say phi. And this has been usually the case, or maybe as is called here as per the notations, it is theta 4. So given theta 2, determine theta 4. Now we can use all those what we call as the So some say let's derive for the forward kinematics. It won't be quite long. Forward kinematics. And since this is a very awkward looking, because the thing is, it may not be satisfying all those. We would not be getting some desired output. So I'll just keep even schematic the way it has been done in the lecture notes, just to be consistent. I'll just we have something like this. This theta for we have link 1 of length L1, L2, L3, and L4, right? Now let's start with, and we fix our origin to be here at this point. So this is our origin, X and Y. So this is our origin. So now let's try to determine the locations of P, and we just call this joint as P and this joint as Q. So the center points of this joint say are denoted by P and Q. So as was discussed in the lecture, our goal is to determine the position, the coordinates of both these points. So we start with say X for point P, the coordinates will be XP and YP. And this is given by, now we take a look. So say these are cosine theta 2, and now XP will be equal to, we know about the projection, right? So the projection is, we want to project this somewhere here, right? So this will be our XP, this will be our projection XP. Ideally, that's what it should be. But say for a general case, because this would always also involve some sign conventions, that's the reason I always I would like the represent to be something along this, although it's not done in the classes, but this is a more, so just even if it's schematic, this looks more easy to analyze. Because when we project it, say we are projecting this here and this is theta 2, then we can clearly say that this is our XP. And XP is nothing but L2 into cosine theta 2. Likewise, YP will be the vertical projection on this projection of this link L2 on the y-axis. So this is our y-axis, right? So it will be YP is equal to L2 sine theta 2, right? Now, since this is done, now let's also look at, you'll wonder why we are not looking at the coordinates of this as well as these two joints. The reason is because they are just constant, isn't it? The locations are fixed. So which means uh, like we already have a very clear idea about what the positions of these two coordinates will be. However, for point Q, we have XQ and YQ. Now let's take a look at this. When we take a look at XQ, then it will already contain the entire link and the horizontal projection of Q, the link with length L4 onto this axis, isn't it? So it will be L3 first, because we are looking at L1 plus L4 cosine of theta 4. Likewise, for when we take a look at X, so sorry, in this case now YQ, that is equal to L1 plus L4 sine theta 4. Right? So we have the projections, and the goal was determine theta 4. Fine. Now let's take a look at. So this will be our link 3. Right. So what we have is we know link 3. We know the value of L3. And we can see from our, say, trigonometry, this Pythagorean identity, Pythagorean identity, that this is going to form a right angle triangle. This part and this part. I'll just mark in a different color. Something more obvious, easy to notice. So it is this part here, right? So this will be a right angle triangle, and we know the value of L3. And this part is the difference between YQ minus YP. And this part is difference between XQ minus XP. So this means that L3 squared is equal to XQ minus XP whole squared plus YQ minus YP whole squared. So this is how it is, isn't it? And now let's go to the next page. So we have L3 whole square. I'll just copy it. So it was XQ minus XP whole square plus YQ minus YP whole square. And upon substituting the expressions, we have XP was L1 plus L4 cosine theta 4. I hope that's right. Yeah, it is here. And then minus, and XP is L2 sine, L2 cosine theta 2 whole squared plus. Now what we have is L1 plus L4 sine theta 4 minus L2 sine theta 2 whole square. Right? Now let's just go on expanding it. So the first this expression is L1, it's like A plus B plus C whole squared. And I'll just write it on. So A plus B plus C whole square is equal to A square plus B square plus C square plus 2AB plus BC, 2BC plus 2CA. Right? So in this case, when we have expand L3 square, the first term on the right, it will be L1 squared plus L4 squared cosine squared theta 4 plus, and then C is minus L2 cosine theta 2 whole squared plus 2L1 L4 cosine theta 4, then plus 2L4 cosine theta 4, and then BC is minus L2 cosine theta 2, isn't it? And then likewise plus 2 C is minus L2 cosine theta 2, and A is L1, right? Now let's go for the second term, and I'll just write the final expressions here, because so it will be L4 square sine square theta 4 plus, since the square of negative number is anyway positive, so it is L2 squared sine square theta 2. And then we have AB, both are positive, so we have 2L1 L4. Both are positive, just what we see symbolically. It does not necessarily be, because sine theta can be negative as well. And we have 2BC, right? So C is symbolically negative, so which means that this will become negative. And then we'll have 2L1, L4 and L2 sine theta 4 and sine theta 2. And then again plus 2CA. So A is positive and C is negative, so it will be minus 2 L1 L2 sine theta 2, right? Now let's say rearrange what all the things that we have. So L1 squared occurs twice. So this and this goes, so it will be 2L1 squared. And then we have L4 squared and cosine squared theta 4 and then L4 squared. And you know that then L4 squared will be common. So it is just using the trig identity cosine squared plus sine squared is equal to 1. So this means it is just plus L4 squared. Likewise for this term, it is for cos squared theta and sine squared theta. So it will be L2 squared. And in this case, it is plus 2L1 L4. And I'll just call it, say, cosine theta 4. I'll just have it and let it be 2L1 L2 sine theta 4. So this is gone, right? And in this case, what happens is we have minus, isn't it? So we'll have minus 2L2 L4 cosine theta 2 cosine theta 4. And then this is gone. And then here we have, similarly, we have minus 2L2 L4 sine theta 2 sine theta 4 is gone. And then we have minus 2L1 L2 cosine theta 2 and then minus 2L1 L2 sine theta 2, right? Now what we know is here there is one very useful what we call so I'll just duplicate this slide. It comes handy. Delete everything, erase everything here, and just keep it till here. Okay. So what we have here is we have what we know. We know L1, L2, L3, L4, and theta 2. So these are the known quantities. What we don't know, not known to us as of now, is theta 4 in this expression. So which means that this will be a constant. This is a constants. So here also only theta 4. So only theta 4 terms with theta, yeah, theta 4 terms we can combine for both cosines and sines because that will be unknown part, right? So why don't we do is that we just say just combine things in such a form that since we cannot express sine in terms of cosine and cosine in terms of sine, so let's just have, say, two blocks, two fractions, so to speak, of the equation. So we have two fractions on one side and the third fraction on the right hand side. So third fraction is that all the terms without sines, without any sine theta 4 and cosine theta is L3 squared minus 2L1 squared minus L4 squared minus L2 squared, right? So this goes, and this is unknown, so it will go here, 2L1 L2. So this goes, and this is also sine, so it will be 2L1 L2 here goes. And this way we have here is cosine theta 2 and cosine theta 4, isn't it? So in this case, what happens is it will, so cos theta, it will go into this club, L2, L4, gone. And here, this will fall in this club, this gone as well. And we should call it cos theta 2, and here it will be sine theta 2. Right? Now what we have is this cos theta 2 and sine theta 2, as you clearly see, does not involve any cosine theta 4 and cosine theta 5 terms. Right? So it will just go here. So minus, it can go on the right hand, it will go to this left hand term in for this equation. Here we'll have what it will write. So it becomes plus 2L1 L2 cosine theta 2 plus 2L1 L2 sine theta 2. Right. So Now what we do is there are several ways of maybe rearranging these equations. So say we can call this A, call this subset as B and this as C, as what does in the classroom. However, we do not directly take this. Say what if there is some say length, say if they are very widely separated, right? Say if L1, L2, L3, L4 are somewhat separated in terms of, say if it's one is 1 meter, the other maybe 5 meters. So say it could lead to some numerical problems, not always, but say if it could, right? So what we do essentially do in such situations is we just non-dimensionalize it in such a way that all the terms become of equal order. So this implies that, say we divide throughout by some factor. Say it could be largest link length, right? Based on, say it will be square of largest link length, or maybe something combination of two other links. So it depends on various ways. Eventually what we say is let's have something of A cosine theta 4 plus B sine theta 4 is equal to C. So this is the form we want eventually. Fine. Now what we do is we given this problem here, A sine theta 4, A cosine theta 4 plus B sine theta 4 is equal to C. So what we do is, but say we have this equation in sines and cosines. It could be very tough to solve it. Of course, there are multiple ways. One way is, say we can divide it in groups like this. Say you have cosine theta plus B by A sine theta 4 is equal to C by A. And this you could write it as cosine theta 4 is equal to B by A sine theta 4 minus C by A. Oh, sorry, it will be minus this. So it's essentially, it will be C by A minus B by A sine theta 4. So this is one approach where what you do is you take a graph, have theta 4 and on the y and the x-axis, and let it vary from, say, minus pi to pi. Anyway, you can always circle back within this, isn't it? By shifting it by 2 pi, isn't it? So eventually we get it. And otherwise, or one way is just, why not have usually a very standard one that we typically tend to use is let it go from, just bound it to 0 to 2 pi. Now what you do is you draw cosine theta 4 graph, which will even start from here, go down, reach here, right? And one graph is for the other case. So this one we call it as, sorry, so this will be, so this is cosine theta 4. And the other graph is C by A minus B by A sine theta. Say it will have some unusual, maybe at sine theta, when theta 4 is equal to 0, then we'll have C by A value, say somewhere here. And then does some, so it's vertically shifted, isn't it? And with some negative value, right? So what we say is it's inverse of sine theta 4. So say something of along these lines, doesn't matter, isn't it? Something along these lines. And you look at what are the intersection points, this and this. So these are the solutions where they intersect. So these are solutions of theta 4. And as you recall, you have two solutions because they will intersect at 2 points. So there is one approach which was not taught during the class, right? And the other approach, what has been adopted in the class is that we take a sine theta 4 plus b sine theta 4, a cosine theta 4, sorry, and b sine theta 4 is equal to c. So the thing is, the previous was from a graphical sense, like this was a graphical approach that we do it, things graphically. But the other approach, which is say more elegant from a mathematical point of view, that we can automate it as well, is that we want to express these two terms. So can we have certain, can we say transform these terms into a certain form where we can express the entire equation in terms of single variable. So there is where trigonometric identity comes in. So the goal is to have a an equation in a single variable by transforming or by expressing sine theta and cosine theta 4 and sine theta 4 in that, using that variable in, right, by expressing in terms of that variable. So that is what essentially I mean. So here is where trigonometric identity comes into picture. And one identity which we had learned during our school years was that if we have, say, cos 2 theta, then this can be expressed as cosine square theta minus sine square theta. So this was one such approach, right, of doing this. And this is one such trigonometric identity. That's what I mean, sorry. And likewise, there were several such identities. And one was one identity was that say we have we had sec square theta is equal to 1 plus tan square theta. And likewise, we had identities such as and of course, the well-known one is sine square theta plus cosine square theta is equal to 1. So there are several such. And then we also have, I'll just write it here, sine. I'll not, as better avoid using theta. It just creates confusion for now. So we'll just call it some phi. So we had sine square phi plus cosine square phi is equal to 1, right? And then we had sine 2 phi is equal to 2 sine theta, 2 sine phi, cosine phi. And now what we do is, say we have this here, this expression here. Say we have tan 2 phi, which is equal to sine 2 phi divided by cosine 2 phi, right? Or maybe what I think I should just approach a different perspective here and say, okay, from here, what we can prove is that we can prove 2 sine phi cosine phi by cos square phi minus sine square phi. Is it not? And what we can have here is this can be expressed as let's divide the numerator and denominator by both cos square theta. So it becomes 2 sine phi cos phi divided by cosine square phi divided by cosine square phi by cosine square phi minus sine square phi by cosine square phi. This cancels out to be 1, and then we have minus 10. Right? So this becomes 2, you will see, right? 2 sine phi by cosine phi divided by 1 minus sine square phi by cosine square phi. And this is equal to 2 tan phi by 1 minus tan square. Right. So this is one thing, what that, let's say we have like of this form, isn't it? So we are able to expand, express tan to theta in terms of tan theta. Now, what we can do is here, so this is in terms of tan phi, right? And let's write it in terms of, say, tan phi. So if tan phi is, then we'll have as if, or maybe let's call it as tan psi. So tan psi is equal to, where psi is equal to 2 phi. So this means that wherever phi is in just in on its own without any pre-multiplication, it will be psi by 2. So we'll have tan psi is equal to 2 tan psi by 2 divided by 1 minus tan square psi by 2, right? So this identity is very handy to us. The reason is, you'll ask is why. So the answer is that, say, given that we know the right hand side, we can write the left hand side as sine phi by tan phi, right? And this will be equal to 2 tan phi by 2 divided by 1 minus tan square phi by 2. And here what you can do is, and it is, so it was sine by cosine, sorry, sine by cosine. So I'll just go to the, I'll rewrite this again. So it is like tan psi is equal to sine psi by cosine psi by sine, sorry, is equal to 2 tan psi by 2 divided by 1 minus tan square psi by 2. Fine. From here, what we can do is we can have it in terms of sine psi is equal to 2 tan psi divided by 1 minus tan square psi by 2. It will be into what? Into cosine phi, cosine psi. And we know the value of cosine psi. So cosine psi can be expressed also as cos square psi by 2 minus sine square psi by 2. Isn't it? This is one way of expressing it. And it can also be written as 2 cosine square psi by 2 minus 1. Fine. It is just by using another identity. So from here, what is our goal? Our goal is to show that we can also write cosine phi is equal to, uh, say, 2 by sec square phi by 2. Oh, sorry. Hmm. So we're here. We can also write in this form, and this can be written as 2 by sec squared psi by 2 minus 1. I know it's going very long, but yeah. So what we can have is, this we can write it as 2 by 1 plus tan squared psi by 2 minus 1, isn't it? And this will be eventually written as 2 minus 1 minus tan squared psi by 2 divided by 1 plus tan squared psi by 2. And this comes to be 1 minus tan squared psi by 2 by 1 plus tan squared psi by 2. Now this is just an intermediate result which comes in handy later. So what you can do is you have 2 tan psi by 1 minus tan squared psi by 2 into 1 minus tan square psi by 2 divided by 1 plus tan square psi by 2. right? And then what happens is this two cancels out. So we have 2 tan, it will be psi by 2. Why did I forget here? Divided by 1 plus. And you know already about cosine. It's of course obvious. It is 1 minus tan squared psi by 2 by 1 plus tan squared psi by 2. So this was the actual derivation, which was just skipped during the class, right? And now we have is our original was that a cosine theta 4 plus b sine theta 4 is equal to c. Right? So what we can do here is that a into, and we were able to express uh, cosine phi, cosine psi and sine psi in terms of tan psi by 2 in both the cases. So what we'll do is I'll mention it here as well. We denote x is equal to tan psi by 2, or in our case it will be tan theta 4 by 2. Right? Right. So you have a a 1 minus x squared divided by 1 plus x squared plus b 2x by 1 plus x squared is equal to c, where x is equal to tan, in this case it will be theta 4 by 2, right? So what we are able to do here is we have now been able to 1a is 1 minus x squared plus b into x is equal to c into 1 plus x squared. And let's bring the otherwise, say we have c plus cx squared is equal to a minus ax squared plus 2b into x. So we have c plus a whole squared. Then we bring b on this side, term containing b, bs, plus we have c minus c. So this is what when we have a quadratic equation, right, in terms of x. So then we use the formula that we have, that determinant, and we call it some a, and this will be, the whole will be b, this will be c, small c. So we have delta is equal to b square minus 4ac, or root over 4ac. So this is equal to 4b squared, and then minus 4c plus a into c minus a is c square minus a squared, right? This we can further simplify as we can bring 4 outside of the square root to have 2 divided by b square plus a square minus c square, isn't it? Therefore, now what we have here is, okay, so what we have here is the solutions will be x is equal to, so as for the formula, minus b by 2a plus minus, it was delta by 2a, isn't it? This was the formula. So b is clearly minus uh, minus 2b, so it becomes plus 2b, right? So it was 2 capital B, and a is equal to A plus capital A plus C. So it is 2 capital A plus C. And plus minus, we have 2, and then the square root of B squared plus A squared minus C squared divided by 2 into A plus C. Right? So 2 cancels out, and we have the solution as therefore x1, x2. There will be two solutions, and it will be B by A plus C plus minus root over, and then I can why should not bring to the same numerator, so it will be B plus minus B square plus A square minus C square divided by A plus C. And then we know that this is equal to tan theta 4, and there are two values, so 1 comma 2. And then we'll determine in which quadrant it is lying. So in which quadrant theta 4 by 2 is lying. So recently we are looking at this, right? Which quadrant this lies. And it will be based on which coordinate, what is the numerator and denominator based on value. And you know clearly that the value is, so here all the trigonometric functions result in positive value. And here only sine gives positive value in the second quadrant, quadrant 1, quadrant 2. In quadrant 3, we have only the what you call tan function, which has a positive value. And in quadrant 4, we have only cosine terms. So based on this position, we determine what can be the value of theta 4. So it's like once you solve this, then we have two values for theta 4. Right? So that is what the goal is, as we learned during this course meticulous, but yeah, this was what, yeah. So we determine theta 4 based on this. So that is means this is what the thing in forward kinematics. Likewise, in inverse kinematics approach that we have to determine given theta 4 what is the value for theta 2, right? And then we have other different cases as well about backward kinematics for this what we call as the 3 revolute 1. So the other mechanism that was discussed is 3R1P. So it's essentially you have it's essentially a derivative of revolute 4R chain only. Oh, sorry, 4R mechanism. Yeah, chain mechanism in which the one revolute joint has been shifted to and made it to be a prism-like, and whose with the two links being of infinite length. I think that was very well demonstrated during one of the lectures, isn't it? So there is L3. This is so this is the value of S, because this S determines how much this is the slider. So that is why I call it prism joint. And this is revolute. This is also revolute. This is also revolute. So we have three revolutes, one prism. And this is the link 3. So which means this is link 1, link 2. Of course, we won't call it link 1, but yeah, let's something denotes something like link 1. And these are offset E. So here the goal is in forward. Given theta 2, inverse given S, determine theta 2. And theta 2 is this angle. This was for 3R1. of type this one for of type 1. And there was another case where we dealt with type 2 chain, in which the mechanism was, the kinematic diagram was, something like this. Yes, input. So here input output goes the opposite way, right? The input is slider and output is this angular displacement. And this is our L1. And this is the offset E. And this because it's connected to stable joint, it can at least oscillate between certain end limits. Right? And this is one such mechanism which is found in say in excavators. So this is one such, as was demonstrated in the class. Right? So this was effectively for the mechanisms. Then we come to planar robots. And we have again two types. It's open chain, and the second one is in closed chain. So these are the two types of planar robots that are going to be taught, and so they exist. And based on degrees of freedom, say for open chain, say let's consider open chain. And based on DOFs, we have that are going to be studied is 2 revolute joints and one with RP. Right. Right. And then based on three DOFs, we have 3 revolute joints, and then the kinematic chain has 3 joints RPR. Okay. So let us look at one such planar 2R manipulator with forward kinematics. Just let it be planar 2R kinematic manipulator, and then let me just draw the kinematic diagram. So there is just the x coordinate system, and you have so the x-axis, and you have say one revolved joint here, the other goes here, right? This will be phi. There's y and there's x. L1, L2. There is some angle given by θ1. Some θ2. Like given θ1, θ2. The goal is to determine xc, y, right? And this is for forward kinematics. You can clearly see that given we provide this two displacements x1 and x2, the end effector, what is the position of the end effector? So this is our end effector. So this is what we call forward kinematics. So the idea is you have xc, and we draw this vertical, and this comes here, and this from the what do you call transverse transversal laws, right, of angles. So we have this to be also theta 1. So you have xc is equal to, and xc is, this is our xc, or maybe from here to here. Now it's composed of two components. From here, this is one component which is L1 cosine theta 1, and this is L2 cosine theta 1 plus theta 2. So xc is L1 cosine theta 2, sorry, theta 1 plus L2 cosine theta 1. Likewise for ye also we have L1 sine theta 1 plus L2 sine theta 1 plus theta 2. So these are the, and we have the end effector angle to be phi is equal to theta 1 plus theta 2 from transversal law, right? So this was for the forward kinematics. Now let's move to the inverse kinematics of the same planar 2 or manipulator. Inverse kinematics. So in this case, what happens is, given that we have xc is equal to, I'll just copy it back again, theta 1 plus L2 cosine theta 1 plus theta 2, and then say ye is equal to L1 sine the theta 1 plus L2 sine theta 1 theta 1 plus theta 2. These are phi, right? And in this case, in inverse kinematics, we know xe, ye, and also phi. So this we know. So what we need to determine is theta 1 and theta 2. And of course, we already know L1 and L2. L1 and L2 are given their parameters. They are fixed structurally. So we have to determine theta 1 and theta 2. Fine. So let's take a look clearly here. We have theta 1 plus theta 2 into, so this theta 1 plus theta 2 is phi, which we know. So this we can also write it as xe is equal to L1 cosine theta 1 plus L2 cosine phi. Likewise, ye is equal to L1 sine theta 1 plus L2 sine phi. So which means that this term is known because L2 is known and phi is known. And in this case, theta is not known. So what we can have is, we can write it as so what we can do here is, we can write it as um, so we can have xe is minus, say, L1 cosine theta 1 is equal to L2 cosine phi, and then we have ye minus L1 sine phi, sine theta 1 is equal to L2 sine phi. And then we can say take the ratio. Then we have L1, sorry, L2 sine phi by L2 cosine phi is equal to XE, sorry, it is equal to YE minus L1 sine theta 1 by XE minus L1 cosine theta 1. And is equal to L2 cancels out. This is also equal to tan phi, which is nothing but theta 1 plus theta 2. Right? Now what we can do is, let's eliminate. So since in this expression here, what we have is, we have uh, like we have an unknown also called theta 2. So theta 2 is unknown and theta is also unknown. So what we can do is, let's make use of certain uh, expression, certain trigonometric identity such that we are able to eliminate theta 2 from the picture. So what we do is, we can have XC minus L1 cosine theta 1 is equal to L2 cosine theta 1 plus theta 2. Likewise, Y minus L1 sine theta 1 is equal to L2 sine theta 1 plus theta 2. Now what you do is, take squares and add. On both sides, when we take squares, so what happens is, on the right hand side, this cosine square plus sine square becomes 1. So we are able to eliminate say theta 1, sorry, theta 2. So we have now XE minus L1, yeah, L1, yeah. So L1 cosine theta 1 whole squared plus YE minus L1 sine theta 1 whole square is equal to L2 squared, right? Yeah, it's L2 squared. So now what we do is, we can again use those same tricks, expand it, but in this case, so it's straightforward, because we have x square minus, or we have x squared plus y square comes it from here. Then we have plus minus 2L1 XE cosine theta 1, and then we have minus, from this side we have L1 YE sine theta 1. Then we have L1 square cos square theta 1 plus L1 square sine square theta 1. So it's L1 square, L2 square. We can rearrange again such that we have 2L1 XE cosine theta 1 plus 2L1 YE sine theta 1 is equal to, sorry, plus L1 square minus L2 square. Now what can do is, divide throughout by say 2L1. So this we can have also call it like, say we have YE sine theta 1. I'm just following the convention in the notes presentation slides for week 3, plus XC cosine theta 1 is equal to XC squared plus Y squared minus L1 plus L1 squared minus L2 squared divided by 2L1. So this we have A, this we call B, and this we have C. And so again, we have the same form. So therefore, again, we have sorry, this A, and this is B, and this term is C. So we have again A sine theta 1 plus B cosine theta 1 is equal to C. And we use all those techniques that was established during the lectures to determine the values for theta 1 in this case. So once we have theta 1, then theta 2 is straightforward, because find theta 1, and then theta 2 is equal to phi minus theta 1. So that's as simple. Then we have planar RP manipulator, and then that's how it goes. So what we'll do now is, let's revisit some of the assignment questions in week 3 of assignment 3 of this course. So I'll do some questions here. So question number 2, I'll just let's have it as assignment 3. Question number 2. So it says that we have a mechanism like this. This is a slider actually, so let me have some gap. And these are line of action, as was discussed in the class. So we have the distance between these two joints hinges as 65 mm. These are theta angle, and there's A, there's point O, and there's some point B. Right, and the distance of the slider is from the ground hinge, which is this here, is S. So it says that we need to determine the value of this distance as from the ground hinge, which means, yeah, as is shown from the graph here, when the crank angle theta, this is the crank angle, is equal to 2 phi. So when theta is equal to 2 phi, and it says also that phi is the crank angle. Phi is equal to crank angle when slider is closest to the ground hinge. Now slider becomes closest to the ground hinge, right? So this is like when slider is closest to ground hinge. And we are also given that the link OA is 20 mm and maximum distance of the slider from the ground hinge. So the maximum distance of this slider from this here, this is the ground hinge. So ground hinge of this slider, this is the slider, is when given as 110. So S max is given as, and for that configuration, what happens is it's the furthest when we have this scenario. When we have this scenario. So then this is S max. So in this case, what we know is from here to here when we go. So this link AOA and AB become, I mean, points O and B are all collinear. So they are collinear points. This becomes A. So from here, what we can clearly see is that now it forms a right angle triangle, right? So this yellow triangle we have. Sorry, not from here. Just from. So it becomes a right angle triangle now. So in this case, what happens is we have S max whole square plus this 65 mm, 65 square is equal to OA plus AB whole square. So this means that we know the value of S max, which is 110. 65 square we know, and OA also we know, right? OA is 20. So AB we will know now from this expression. So this means that AB is very clearly, after doing calculation, because 107.77 mm. Fine. And it says that once we have this, now it says that, uh, and it also says that phi is the angle when the slider is closest to the ground hinge. Now the closest this slider can go is in this configuration. So say we had this configuration that initially, and let's bring this more forward. At one time, this will also gradually become something like this. Then furthermore, and at one time it will be coincident. And after that, it cannot go to the other side, right? There was some, as we learned in our class, that there is some issue that this line cannot pass anymore to the other side because of this length constraints. Now it cannot pass through the other side, which means that it cannot, like this cannot become the link connecting this hinge to this slider cannot be of this situation. Now it cannot cross. Our scenario when we have say so we have this ground hinge, so this is the maximum possible. This is when the slider comes closest. Come on, sorry. So this is the when it comes the closest, the slider comes closest to this. So this angle is what we have is phi. This angle we call as phi. And the distance, this is anyway fixed as 65 mm. And we already know that AB, so this was OA, there's B. So AB was 107.77 mm, right? And then we have, sorry. And then we clearly have that OA is given as how much? It was 20, right? Mm. Then in this scenario, OB will be equal to AB minus OA length. So it becomes 87.77 mm, right? So this is 87 mm. Now from our trigonometric identities, what we are able to show is that tan this angle, say we call it some psi. So tan psi is equal to how much? Tan psi is equal to, not tan psi. From this graph, we can see that sine psi, because it all involves perpendicular but hypotenuse. So it becomes sine psi is equal to 65 by 87. Isn't it? So this means that psi is some angle. So it's around 0.88 and 1, and then say 4 degrees. So because of which, so this is psi, so this is also be psi, and phi is equal to 180 degree minus psi, which is essentially equal to 32.22 degrees. Now we are asked to determine, now we have theta is equal to 2 phi, which is equal to 264.44 degrees. And now we can use the displacement analysis. Of 3R 1P chain 1 mechanism, since it is 1P chain 1 mechanism. There is chain 1 mechanism. And here what happens is E is below this, below the origin. So here E will be, this is also equal to magnitude of E. So here E is equal to minus of 65 m. But because the thing is, for the chain, what we had is the slider used to be above the line of action, so somewhere here. So in that case, uh, it was E was positive, so this used to be the E. But in this case, it is below the line of action, so this is the line of action below that, right? Or not even line, it's just some, yeah, it's just below this, so we just call it minus, right? It's like minus value. And then we can use all our displacement angles. And when we have this formula called S2, S is equal to L2 cosine theta 2 plus minus L3 squared minus L2 sine theta 2 minus E whole square. So this was the function. And based on, we take two values, and then we, in this scenario, we call, we'll take the value with, since it's coming towards the ground hinge, so we'll take only the positive value. So S2 greater than 0 is considered, which is essentially equal to S2 is given as 95.94 mm. So this is what we do here, right? And one more problem we'll do. I think we are uh, lesson 5 of the assignment. So in question 5, we had this mechanism here. And then we have one line which crosses through all this. For it as theta is equal to some 70 degrees. L2, L3, L4. This was L5, and this was S, the slider. So here determine S. So S is not known, and we are given L1 is equal to, this is L1, 700 mm, L2 is equal to 300 mm, L3 is equal to 450 mm, and L4 is equal to 600 mm, L5 is equal to 750 mm. So what will be the approach? Solve this problem at first. So first of all, what we see is this is a 4-bar linkage. So it's like 4R, and it is connected to 3R, 1, 2, 3, and this prismatic joint here. So we have 3R1P chain, isn't it? Okay. And as we learned, the offset here is 0. So offset is 0. So E is 0 because of this ground hinge and the slider hinge are at the same level. So offset is 0. Fine. So what we'll do is, this is our theta 2 and this will be our theta 4. So our first is determine theta 4 and then determine S. So which means that it's forward kinematics problem. So given theta2, determine theta4. Once you have theta4, that is determine. Yes. So this forward kinematic problem for 4R chain is like 4R, and this is 3R1P. And this is the problem for 3R1P of type 1. Right. So this is what it is. Like this, the philosophy. Rest numericals is anyway straightforward. We have to use the formulas. So I think, yeah, with this we have done some of the solution part for today. I'd very much like to do ANSYS, I mean this MATLAB's problem today, but it seems that we have done enough material for today. So I'll just show you, like, this is one of the code that I had written to solve the assignment 3 problems. So here I have just used all those. Maybe I should just open it using some other say Visual Studio. So I have just used this codes for forward kinematics for every problem for 4R chain, and then the forward kinematics for 3R P1 for 3R1P. It is essentially. So this chain, if you want, if any one of you would like to say take a look at how to use some basic functions. So this is one such code that I written for solving some of the problems of assignment 3. So yeah, I think there's not much to be done right now. So yeah, I think let's call it a day for today. And let's meet during the next session. So I'll just close the stop recording.